So I'm going to show you how to install oooark from the beginning using the Git repository. So this is kind of a long URL to remember, but you can just look up oooark on the web and then get the SourceForge address for that. Let's see. Oops. So this will be a short tutorial on how to install oooark, how to get it running, how to use the toolbox, and shows some of the features with a demo that I've just created. So once you've got the Git repository, you have just to run the auto build script, and then gives you a couple options. If you're using Debian based operating system like Ubuntu or Debian, you can grab Debian dependencies, and that should get most of the install dependencies that I've realized at this point. Then you can use CMake, through the auto build script again, just do in-source build, option 1. And that'll use CMake to download everything for you. I've got it automatically pulling the other Git repositories, so make sure you have Git installed, and you'll see that it grabs Mavlink, it grabs JSPSim, whatever else it needs. Mavlink, it'll pull the Git repository if you don't have Mavlink installed. The same thing with let's see, boost numeric bindings, which it's another package. So you can see right here it's cloning the boost numeric bindings repository. And you can see it successfully got the Mavlink source as well. Okay, so then it's gone through and built all the source files, and then it's actually calling scicoslab here to build all the blocks. So at this point you're ready to go. If you want to create a Debian package for your operating system, you can go into build and do cpack-g deb. That's the manual way, so you can create a cpack-g nullsoft installer if you're on Windows. Okay. If you're on Debian, through the auto build script, I've got package, which will create the Debian package automatically. So when you use cpack, all the packages that it builds are going to be found in the build directory. So cd build, and then you'll see oooark 020. So if you wanted to install that into your system, do it like this. Now that's going to automatically install the files. You can see into user lib, scicoslab, into the contrib folder, and that'll let you load it as a toolbox. And you can see it's got all the demos installed as well. So in order to use it as a toolbox, you can use your scicoslab installed on your system, and then you can have this toolbox button. You click that, and that'll load the toolbox for your use. So if you click on demos, you should be able to see all the oooark demos here, and I've got a little menu that pops up. You can see like the backside autopilot. So this is using JSPSim to model EasyStar data from the wind tunnel that we got, and when you run it, you'll actually see the open scene graph visualization here, and then you have the control over the autopilot. This is the altitude, this is the velocity, and this is the heading. So you can see it's commanding 180 degrees heading right now, so it's turning around. And all the models for the visualizations are all done in Blender. So you can see I commanded 69-degree heading, and it's going to that. So shut this down. So those are the demos that exist in right now that you can go through. You can see some other ones. The trim demo, it's showing the trim feature, showing that it's actually trimming it correctly. Okay. So to see the development stuff, though, it's not all distributed like that yet. So if you don't have it installed in your system, you can just run scicoslab here, and then that'll run the scilab.ini that's in the Git repository. And this tells scicoslab to load the toolbox found in the current directory, which is going to set you up anyway, just like it was installed. It's going to call this loader script, which is going to load the toolbox, and then it's going to start this demo for the Arducopter, which is one that I haven't put in the main demos yet. So again, if you're using the installed version on your operating system, you can go through toolboxes, then you start up Psychos. Then to actually start using the palette, use Paletry. Palettes doesn't work right now, so just use Paletry. You can scroll down and see all the orc blocks. So some of the new blocks that I've put in here, EOM 6DOF. Nicholas and I have been working on this one, and you can select either the wind or the body frame, and it changes the equations of motion that it's using. If you click on help, we've been trying to do a pretty good job of documenting all the blocks so that it's easy to use. You can see here the first input is the force in the body frame, and then the moments in the body frame, and then the mass and inertia properties. And if you're in the wind mode, your state is described by these these variables, and then if you're in the body mode, it's described by these. And then it outputs the state, which is just the time derivative of all these components. So using that, you can construct equations of motion for a vehicle, and I'll show that later on in the demo. Some other things like Euler to DCM, so that helps out a lot. Flight gear comm isn't working right now if you're using flight gear greater than 1.0, but if it's 1.0 or lower, it should be fine. Geomag is basically talks to the world magnetic model and outputs the magnetic field. And again, on stuff like this, you can always click the help button, and it should show you the full details. Like this takes inclination, declination, and then the magnetic field strength are the outputs, and it takes the lat long and the out that you're at. Okay, GPS INS is a block that's trying to use some LAPACK libraries itself. That's not quite working right now, so ignore that one. GPS mag measure model. This is a linearization of magnetometer measurement. So we can look at that. So this can be used for doing Kalman filters with magnetometers. INS dynamics. Again, this is for Kalman filter use, linearization of the navigation system. It's got a couple modes. You can see that there's an attitude mode and a velocity mode, or velocity position mode. So that's just which states you're using. If you're in the attitude mode, it's the quaternions. In the velocity position mode, it's the velocity in the position. So you can go through that and look at our source code if you want. So this inverted pendulum here is just an example that was from the book. JET is the visualization of the jet. JSP SimCom actually allows you to talk to JSP Sim, so you can use XML-based aerodynamics files and stuff for full models. This is how we've modeled the Easy Star aerodynamics in the wind tunnel. Okay. Now here's all the Mavlink stuff. So you can see the Mavlink HIL sensor. Now this lets you specify the port you want to talk over and the baud rate, and then it passes all these arguments so this is an input from the autopilot, Excel, gyro, mag, GPS, and then the output is lat lon out. So this is for the sensor-based hardware in the loop, and for state-based hardware in the loop where it's not as detailed, the input to the block is going to be basically your current state, and then the output from the autopilot is the normalized servos. So this one's been tested with ArduPilot Mega, but hasn't been updated for about a month, so it might be out of date with the latest trunk. I think this is in development. So plane visualization of the plane that we saw before. Quad force and moments, it's in development. Quad is the Quadrotor visualization. Quad Euler to DCM, this takes quaternions and converts them into direction cosine matrix. And it also handles the rates for you. Alright, rand-in, we had some issues with the standard random generator block, so we created this one that takes in as an argument one of the states. Alright, this is a waypoint guidance block, pretty simple. I don't know if we've done the documentation. Yeah, we have. So it takes the latitude, longitude, altitude, and velocity of the destination, and it takes the current state, and it outputs all the commands to the autopilot system. Okay, and we created a zero order hold block that's a little bit different from the other one. Gives you some more options here. Alright, so those are an overview of the current blocks. Now I'm going to go to the demo that's in the development repository. So if you're in the org get repository and you type scicoslab, that uses the scicoslab ini folder file sitting right here to launch scicoslab. That creates and launches the toolbox. And by default it's going to start the Arducopter right now. So Arducopter demo, if you look at the context, and all the diagrams can have a context, so at any level it's basically anything below that level will have the same context defined. So if there's a variable, it's basically scoped. So if there's a variable at this level, everything underneath it, all the blocks underneath it know about that variable. Now if I create a variable here, then anything in this level wouldn't know about that variable. So at the very top level I've created a bunch of global variables basically that describe the quadrotor, so you can adjust it for your own quad and your own data. So here just some basic constants. The trim conditions that we want to start the quad at. Alright, aerodynamic properties. These are all really pretty rough right now, so we're going to try to get out to the wind tunnel and get some better data. Airframe properties, again, the inertia is pretty rough. We're just estimating right now. The motor, we've got some good data, so I'm fairly confident on this. At least for the older or the smaller Arducopter motors, this is the data. We took it basically a load cell and measured the maximum thrust, and then backed out from a paper on Quadrotor propulsion systems, backed out the thrust coefficient and torque coefficients. This control period is used to model the discrete time effects on the control system and try to make the control system robust to that. But in this context it's not used. The T-sum trim is basically the sum of the motors, and all motors vary from 0 to 1. It's all normalized. So if the trim value goes from 0 to 4, 4 would be the motors are all on. So 4 times 0.5 is 2, and when the motor's all the way off, it'd be 0. So it goes from 0 to 2. I'm sorry, 0 to 4, but the trim is about 2 because it's 0.5. So at hover, of course, all of our velocities are going to be 0. Our controllers here were all designed using the linear approximation of the system, and you can see we put basically a low pass filter at 5 Hertz, and then we're using this lead compensator, and the lead compensator is basically a 0 at the motor pole, and the gains were just adjusted to get the bandwidth that we wanted. And you can see the actual linear design right now if you go to the tree and go to the theory section, and you can type let's see, go ahead and start scicoslab in this folder, and then if you type execute Arducopter, and that shows you our current design. So you can see all the Bode plots and step responses, the steady state DC gain and steady errors and all that stuff. Alright. So I was playing with this one. That's a PID with a low pass filter on the derivative gain, but not really using it right now. So this hasn't been tuned and optimized, so it's still in development. Now, let's see, if we go to the controller and take a look at that, to actually do the nonlinear control system, I've put the control mixing here, and then these are all the transfer functions, and then the saturation of the control system actually occurs in the dynamics here. So if we take a look at just like the side velocity controller or forward velocity controller, so here's forward velocity coming in, the feedback of the forward velocity and all the other parts of the system, and then the output of this loop is the front-back ratio for the motors. Okay, so then it's actually front minus back, 0 to 1 on motors. So then you take in the command forward velocity, you fed back the forward velocity, that gives you an error in forward velocity. So this transfer function is from forward velocity error to theta, which is your pitch angle, and then that's subtracted from the actual pitch. It gives you pitch error. Then you get error in pitch to the commanded rate, the pitch rate. So then you subtract that from your actual pitch rate, and then through another transfer function to the front minus back pseudo input for the quadrotor. So you can see each of these transfer functions are just basically taking the numerator and denominator of the global that I've defined for each of these. So it makes it nice to have all those transfer functions at the top context. So when you're doing your design, you can do your linear design and then just plug these in here once you know what you want, and then test it. So you click OK, and then it's actually going to execute this little script and define all the variables. So that's the controller. Now we'll take a look at the dynamics block, and using that 6-degree freedom equations of motion block that we've just created. So here's the EOM6 DOF, and if you look at this, you get the option of the wind or the body set, and you can click on the help button here and get more details about that. Again, we've already gone through this, but you know, the wind mode, body mode has different dates. Now, I told you this can be used to make the equations of motion for a vehicle. So basically, if you plug the force and moments from any vehicle you want, if you can describe those into this block, and then you integrate the derivative, and then feed that back, and this is the state, then you basically have the dynamics for whatever vehicle. Here we have the mass properties, so the mass, and then all the inertia matrix components. We're neglecting some of these because in a quadrotor these are all going to be 0. Okay. Quad force and moments. We basically have the aerodynamics and the propulsion system, and then the gravity model. So for the aerodynamics, we're using a little sci-func here that basically takes in the body velocities and then computes the true velocity, and it computes alpha and beta. And then there's just a check here if you're close to 0, it doesn't try to take the ATN to avoid a singularity. So sci-funcs are useful for doing little things like that that would be horrible in a block diagram. Alright, so then we go into the aerodynamics, and then there's these little tables that are really helpful, and you can actually launch a graphics window here. And so here's our lift curve. So if we just want to create some data on the fly, it's really helpful. Left click and it creates a point. You can drag it around. Double or right click on a point deletes it. So right now we just have basically a straight line. And then it saturates. You can select whether you want to extrapolate at this point or if it just gives you the value at the end, and that's what I've got it set to. So if we go off the chart, it just stops at this value instead of extrapolating. Alright, and then another cool feature is if you're in this mode, you can tell it to load data from a text or an Excel file. So that's pretty useful. Alright, and you can exit without saving for this. Okay. Right now I've got all the coefficients for the aerodynamic moment set to 0. That's because we haven't measured them yet, and I don't think there's a significant effect at this point until we have a higher velocity. And then this is just estimating the dynamic pressure. Alright, so I've described the aerodynamics block, and then the propulsion, I've just read some papers on modeling the electric motors with a prop on them. And I found these equations. Again, if you go to Maxima, you can find those equations and see where my source was. Okay, so now we're actually going to get this to run. Let's go ahead and show you the Maxima file. So if you want to check out any of the theory for this project, most of it's in Maxima and it's auto-generated. So if we look at the Quadrotor force and moments, so Maxima is a pretty useful program. I've written a little common file that basically describes a bunch of direction cosine matrices and stuff like that. So I'm going to run it, and you can see it generates all of the theory for us. Cool thing is it actually generates Fortran 90 code at the bottom, and Fortran 90 isn't directly useful for us, but it does write it into a format that can be easily translated into C++ and scicoslab, especially if you're using the Boost library for C++. So I'll show you that. So here's the source, and then the equations for the thrust and torque coefficients, all that for the quadrotor. Alright, so now I'm going to show you the Fortran 90 code that was generated. So here's the quad force and moments Fortran 90 file, and you can see that's what that code just generated for us. So if we don't want Fortran 90, we can just use a little bash script that I created here. And it's basically really simple. You just cat the Fortran 90 file and then just dump it into a sed command of your choice. This can probably be done in a better way, but I haven't played with it too much yet. This seems to work for now. Alright, so take the Fortran 90 file, do a bunch of set operations, and then dump it to your header file in C++. And also that we've done that for scicoslab as well. So this one creates a scicoslab file. Alright, so we have looked at the theory for that block. At some point, I'm thinking about, having a variable battery voltage. I mean, it's sitting there so we can look at the effects of that on the quad as well. Make sure that it doesn't go unstable. Going ahead and running the simulation now. So you can see we have the dynamics here, the controller feeding into the dynamics. This is my user input. These are little scales that you can play with. So if you right click on these, it's always double click sometimes is not as easy as just right clicking and clicking open set on the block. And then we can set the range here and then what we want to divide by. So this is going to let us vary the forward velocity from 10 meters per second to negative 10 meters per second. If I put 10 here, that would be negative 1 to 1 with 10 increments each side. So we'll just leave it at 10. That seems fine. The altitude, I don't want to go off the scale, so I'm just going to make that about 10 meters. Velocity for the side velocity is fine. For the heading, it's negative 180 to 180, and this is what it divides by, so it's a little bit backwards, but that gets you into degrees. So if we run it, I'm plotting the command arrow over here, and zoom in a little bit more. Make this negative 5 to 5 about. And motor input. Let me zoom in. The trim is around 0.5, so if we look at like 0.3 to maybe 0.8, see a little more movement. Okay, so here you see Open Scene Graph start up, and it's got your visualization. If you right click and you drag, you can zoom. Left click is rotate. And if you middle mouse button click, you can pan. If for some reason you get lost like this, and you don't know where you're at, you can hit the space bar, it recenters your view. Okay, so now we can look at the motor input, the command error, and then we have our little input scales that let us basically act like the guidance system for the Quadrotor right now and make sure the control system's working properly. So I'm going to give it a step input into the heading command. So we're commanding 100 degrees. The red is actually the forward on the quad. So I commanded negative 100 degrees, and you can see the response is followed there. Alright, we'll take it back to 0. Okay, I think my scale factor's off, so I'm going to stop the simulation. So this should be 180, I think. So now if we try that 90 degrees, it should basically turn a right angle for us. There you go, that's right. So now if we go commanded to go back the other way, should be a 180 degree turn. And you can see that the control system does a good job of, decoupling the motion. You can see that these are the two motors, and basically they're exact mirror images of each other so that they don't cause any kind of torquing that's not desired. So now we can show the heading works. Let's try some forward velocity. Command 4 meters per second forward velocity. You can see the response here. Alright, so forward velocity should be, oh, a little instability. Let's do, oh, that's too far. So something I haven't really worked on yet is the saturation occurs. And if you get locked up like this, I think there's some bug right now in the code. Yeah, we got not a number somewhere, so you just restart it. Nice thing about the INI file is it'll always pop it up where you were. And since this is all in development now, saving often is a good idea. So let's not try such a drastic input here. Let's try, let's get our windows back. Forward velocity of 2. There we go. So I think a lot of the problem on the control system right now is the saturation levels. As soon as it saturates, then the ratios between the motors aren't held, and then you get problems. I mean, this isn't zero steady state error, so that's a little could be an issue. All right, so let's try taking this back to 0, and then hopefully it'll work correctly. So we might need an integrator and a feed-forward path there. So that's looking good. All right. Oh, still some overshoot. That's a little weird. Let's try heading response again. That looks pretty good. You can see that symmetric behavior. Okay. Now let's try an altitude step. So since this is just an attitude representation, you can't really tell the altitude steps occurring, but it is. So I think we ran out of time. Yeah. So let's try a side velocity increment here. Okay, that's looking pretty good. Still got a lot of overshoot though. Whoa. Bring that back to 0. Oh, we lost it. Alright, well, I think that's it for right now. We got some work to do still, but it's looking pretty good.